Welcome back, everybody. In this section, we'll be working on sampling distributions and estimators. This is section 6.3 in our textbook. So we'll start with a little definition. We're going to talk about what a sampling error is. We've talked about how in reality, we don't have always an easy way to find out information about a population, like the mean height of all COD students, or it's also at times impractical or impossible to sample every member of a population. You're not going to go and take a bite out of every hamburger your restaurant makes in order to check the temperature, right? Or to check the flavor, right? You're not going to sell many hamburgers with a bite taken out. So you can't check every single one. So you take a sample, you take a look at the sample, and based on the sample, you make some decision about the population. We've talked about that a number of times. The sample that you take, even if we follow all the rules that we talked about in chapter 1 as far as making a good sample without having any kind of bias or anything, even if you follow all the rules about choosing a sample, the sample won't necessarily be the same as population. And that difference between whatever population parameter you're studying and the corresponding sample statistic, that difference is called sampling error. So the definition you're seeing on the screen here in purple, the error resulting from using a sample to estimate a population characteristic. And here the phrase sampling error, usually we think of the word error as meaning like a mistake, like you could talk about the errors you've made on your test or something. But here the word error is used a little differently, and it just means the difference between what the sample value is and what the population value is. It's more like, has in common with like measurement error you might learn about in like a chemistry or physics class. It's just a difference between two values. Okay, another definition, and this one is a little longer and complicated, but we'll be careful. The sampling distribution of the sample mean is the distribution of all possible sample means, or the distribution of X bar, with all samples having the same sample size n taken from the same population. So how to describe that? Think about a population of, we'll use COD students because it's familiar. So the whole population will be all COD students. And let's take n to be 20 for this. And we're interested in how many units those 20 students are taking, like on average. So the mean number of units the students are taking, and we're taking groups of size 20. So think about taking all the possible groups of size 20 students. I could select, for example, 20 of you. We could select a different 20 of you. We could select the 20 tallest people in the class, the 20 shortest people in the class. We could select one person from our class and then one person from 19 other classes. We could make a lot of 20-person groups. Each of those 20-person groups is going to have a mean. And so what we can do is we can look at the distribution of what all those sample means are. So picture every possible group of 20 COD students, and there's a lot of them, right? And each of those is going to have a mean. What that distribution of those sample means is what's called that sampling distribution of the sample mean. So looking at the box towards the left of the screen, we're going to randomly select n values and find the mean of those values. And so for our first group, we'll have X bar 1, we'll have X bar 2, X bar 3, and so on. We can make a table, we could make a histogram, or in some cases, we could produce a formula that describes what those distribution of sample means are. And a big deal is that the mean of all those sample means is going to equal mu, which is the population mean. So an easiest way to see how all this is working is with a population that is much smaller. So we're going to try that right now. So let's just take the population of numbers 1, 2, and 6. So just 3 numbers, a set of numbers containing 1, 2, and 6. So our first task is to find the mean for this population. So 1 plus 2 plus 6, we're dividing by 3 because there are 3 numbers. Sorry, I have my other mode on here. So 1 plus 2 plus 6 all over 3. So that's 9 over 3, which is 3. So the mean of this population 1, 2, and 6 is going to be 3. All right, so now we're going to take all the 2-element simple random samples with replacement. So take that population of numbers 1, 2, and 6 and think about all the ways that you could choose 2 of those items. So, and this is done with replacement. So 1 and 1, 1 and 2, 2 and 2, 6 and 6, 2 and 6, and then 1 and 6. So all those possible samples of size 2 with replacement are shown down below in green. Okay, now we're going to find the means of those samples. 1 plus 1 is 1. Sorry, 1 plus 1 is 2. Divided by 2 is 1. The mean of 2 and 2 is going to, of course, be 2. For 6 and 6, it will be 6. For 2 and 6, it will be 4. For 1 and 2, it will be 1.5. And for 1 and 6, it will be 3.5. Okay, so make sure that you're knowing where I'm getting the mean of those samples. Now we want to find the mean of those sample means. So I'm going to add across the first column and then the second column. So we'll have 1 plus 2 plus 6 plus 4 plus 1.5 plus 3.5. And there were a total of 6 samples. Okay, so adding across the top, I'm going to start from the right because it's easier for me. So there's 4, 5, 15, 18 in the numerator. That's divided by 6, which is 3. So that is the mean of those sample means. And so you'll notice that the mean for the original population, which is 1, 2, and 6, that mean worked out to be 3. The mean of all those sample means is also 3. That wasn't an accident. That's what it's saying here. If we take all the possible samples of a certain size and calculate their means, if you take the mean of those means, you're going to get the population mean. It turns out that that isn't true for every possible statistic. And so that leads us to yet another definition. We want to talk about the difference between a regular estimator and an unbiased estimator. So an estimator is a statistic that is used to infer or estimate the value of a population parameter. So the range or the mean or the variance, we can look at a sample range, mean, or variance and use that to tell us something about the population mean or variance or range. The sample statistic may or may not represent the population parameter well. If it represents it well, it's an unbiased estimator. So an unbiased estimator is a statistic that targets or represents well the value of the population parameter, meaning that the statistic has a mean that is equal to the mean of the corresponding parameter, like we saw in our example before with numbers 1, 2, and 6. We're going to try it with the range. We'll keep the same population, 1, 2, and 6. So let's find the range for that population. So range is the maximum minus the minimum. 6 minus 1 is 5. So the range for this population is going to be 5. Okay. Now we're going to find, well, again, we have all the 2 element samples. As before, we're going to find the range for all of them. So let's do that. So there's a range of 0, 1, and 5, 0, 4, and 0. Okay. Now let's find the mean of all of those ranges. Zero, 1, 5, 0, 4, and 0. And again, there were 6 of them. So we have 10/6. That's 5/3, or about 1.6. Okay, you'll notice that that mean is nowhere near the range of the whole population. The range for the whole population is 5, but the mean of the sample ranges was 1.6. So what that represents, or what that gives you, is that going around and taking samples and calculating those sample ranges is not going to give you a good idea of what the population range would be. In the same way that for the mean, it was a good estimator. So that is the difference. So the range is not an unbiased estimator. The mean was an unbiased estimator. Okay. All right, some more words. All right, so all the examples in this section use sampling with replacement. We talked about both sampling with and without replacement in chapter 4. Sampling without replacement has a good practical advantage of avoiding duplication whenever the same item is selected more than once. We often do sampling with replacement for a couple of important reasons. When you are taking a small sample from a large population, it doesn't make a significant difference whether we sample with or without replacement. If you're going to be choosing 5 people out of all of the people who live in Coachella Valley, if you're doing the sampling with replacement, or without replacement, it's pretty unlikely that you're going to get one of those 5 people a second time, just because there's so many people who live in the valley. So it doesn't make a lot of difference. We talked about this in conjunction with the 5% rule for cumbersome calculations. When you do sampling with replacement, that gives you independent events. And we talked about how when you have independent events, the formulas are often easier to calculate with. So for that reason, a lot of times we treat things as if they're independent, even if they're not. And a lot of times in real applications, the sample size is relatively small compared to the size of the population. Okay, so we had mentioned this already. The sample range is not an unbiased estimator of the population range. Sampling distribution of the sample variance. So this is similar to what we did with the mean, only instead of taking the mean of all the samples you've collected, you're instead taking the variance. So formulas for the standard deviation and variance are shown. The sampling distribution of the sample variance is the distribution of the sample variances with all the samples having the same sample size n. So you have to be taking the same sample size all the way through. So then important things to note: the sample variances target the value of the population variance, meaning that the sample variance will be an unbiased estimator, which is good. The mean of the sample variances is the population variance. So if you go out and take a bunch of samples, select n values and find the variance s squared, and make the distribution of all those little s squareds, the mean of that distribution is going to be equal to sigma squared. We have a sampling distribution for proportions too. The sampling distribution for the sample proportion is the distribution of sample proportions with all the samples again having the same sample size n taken from the same population. We have symbols for proportion, so it's going to be p again. P is used a lot in this class for different purposes. Here's one of them. We used P for probability back in chapter 4. We can also use P to represent the proportion of something. For a population, it's going to be a lowercase p. For a sample, it's a p with a little hat on top, or a caret. So this p with a little thing on top, that is called a caret, not like the vegetable. It is C-A-R-E-T. Sorry, my pen is messed up. The hat on top is called a caret. And if you're typing, it's going to be a shift 6 on your keyboard. And basically what this is doing is telling us that we're dealing with a sample proportion. You'll notice that this kind of deviates from the way that we were doing things before, of having like a Roman letter for the sample standard deviation and a Greek letter for the population standard deviation, a Roman letter for the sample mean, and a Greek letter for the population mean. For proportion, we're not doing that because the Greek letter for P is going to be pi, right? So we wouldn't want to see us going around with like P for the sample and then pi for the population, just because pi has like so much baggage in math having to do with like, you know, circumferences of circles, that we don't want to start using pi for something else. Okay, so for that reason, our scheme of things of having, you know, Greek letters for population is different here. For a population proportion, it's going to be a p. For a sample proportion, it's p with a little hat on top. And so we'd say this as p hat. That's the sample proportion. Okay. Examples of the notation here. It turns out that out of all COD students, about 57% are female. So if we're taking COD students to be the population, P is 0.57. That's the population proportion, or 57%. In this class, it's 21 out of 35 students, and that's 0.6 or 60%. So right around the average, right around the same proportion of COD students as a whole. For proportions, the sample proportions also target the value of the population proportion. That is, the mean of the sample proportions is the same as the population proportion. The distribution of sample proportions is approximately normal. So again, what this is going to mean is if you take a whole bunch of samples of a certain size n, and calculate all those proportions, each one is going to be a p hat 1 for the first sample, p hat 2 for the second sample, and p hat 3 for the third sample, and so forth. If you make a distribution of all of those proportions, the mean of all of those p hats is going to be p, your population proportion. Okay. So we've talked about unbiased and biased estimators. The mean and proportion are unbiased estimators, as is the variance. We saw how the range is a biased estimator. We didn't talk about the median, but it is a biased estimator. And the standard deviation is also a biased estimator. It's still commonly used just because the the variance has squared units on it, whereas the standard deviation does not. So for that reason, we still use the standard deviation, and we have some workarounds to deal with the fact that it is not an unbiased estimator. All right, so our last example has to do with proportions. So for this one, we have the numbers 1, 3, and 8. And here we'll read off the story. It says 3 randomly selected households are surveyed. The numbers of people in the household are 1, 3, and 8. So 3 households, one had 1 person living there, one had 3 people living there, and one had 8 people living there. And so it says we're going to take samples of size 2, and we're going to take them from with replacement from that population. We're going to construct a probability distribution table that describes the sampling distribution of the proportion of even numbers when samples of size 2 are randomly selected. Okay, and then let me do that, and then we'll talk about the rest of the question. So for population of 1, 3, and 8, I've listed out all the possible samples of size 2. 1 and 1, 1 and 3, 1 and 8, 3 and 1, 3 and 3, 3 and 8, and then 8 and 1, 8 and 3, and 8 and 8. So we wanted to know the proportion of even numbers. So there's 0 here, 0 here. Half the numbers in 1, 8 are even. 0 here, 0 here, half are here, half are here, half are here, and all of them are. All right, so out of the 1, 2, 3, 4, 5, 6, 7, 8, 9 possible samples of size 2, how many have 0 even numbers? 1, 2, 3, 4 do. So 4/9 is the probability that we will have no even numbers. There's 1, 2, 3, 4, 4/9, the probability that we'll have half the numbers being even. And then finally 1/9, the probability of 100% even numbers. Okay, there's our little probability distribution. Does the mean of the sample proportions equal the proportion of even numbers in the population? So the proportion of even numbers in the population is 1/3, right? The population is 1/3 even numbers. It says, does the mean of the sample proportions equal that mean? So let's take the mean of all of these sample proportions. So that's 0 plus 0 plus 0.5. There's 2 more zeros, 3 of the 0.5, and then a 1. And then we have 9 of them. So adding that up, 0.5 plus 0.5 is 1, 2, 3. 3 in the numerator, 9 in the denominator, and then of course 3/9 simplifies to 1/3. So what this is showing is that the mean of the sample proportions is the same as the population proportion. So all of these, the 0, 0.5, and so on, that is our set of 9 p-hats of sample proportions. And we saw that that ended up equaling, or the mean of those ended up equaling the population proportion. All right, that takes us to the end of section 6.3. The idea of sampling distributions takes a little getting used to, but we will end up using that kind of for the rest of chapter 6 off and on, and then also off and on through the rest of the course. So make sure that you're reading the textbook, and let me know if you have any questions, and have a great day.